उधर कैसे सिचुएशन?
सर ठीक है, अभी आईआईटी मद्रास तो अभी क्लोज है।
हाँ, 100 पार्टिसिपेंट्स, 100 सॉरी नॉट पार्टिसिपेंट्स, 100 पेशेंट्स है।
100 अराउंड 120 और 150 अराउंड सर।
ओके। नहीं, परसों
हाँ।
परसों श्रवण कुमार सर किया था, दैट ही वाज टेलिंग पूरा इंस्टीट्यूट लॉकडाउन कर दिया।
बट स्टिल स्टूडेंट इज देयर सर।
ओके ओके। We'll start in a minute actually. Then I will introduce.
ओके सर, सर सर। आई होप सर ऑल द सेशंस went fine sir.
Yeah, yeah, went fine. Only participants only should tell now whether they are good or bad or worst. So they will be giving some feedback. Let us see. Chalo, we'll start actually. So, good morning, everyone. This is the last session of the MMM 2020. So, the next speaker for today is Dr. Jitendra Katyar. Let me introduce him. So, Dr. Jitendra Katyar is presently working as a research assistant professor in the Department of Mechanical Engineering, SRM Institute of Science and Technology, Kattanukkulatur, Chennai. His basic research interests, which include tribology of carbon materials, polymers, self-lubricating polymers, lubrication tribology, modern manufacturing methods, coatings for advanced techniques. So he obtained his bachelor's from UPTU technically, and his master's and PhD are from IIT Kanpur. Dr. Katyar is a life member of Tribology Society of India, Malaysian Society of Tribology, Institution of Engineers India, ISTE. He has authored or co-authored more than 60 publications in reputed international journals and conferences. He published 2 books such as Automotive Tribology and Tribology for Materials. Automotive Tribology and Tribology in Materials and Applications in Springer. And he has also written Engineering Thermodynamics by Kada Publications. There are 6 books which are coming very soon. They will be in the market from CRC Press and Springer Nature. He's a guest editor of special issues on tribology materials, surfaces and tribology materials, surfaces and interfaces, lubrication science, Journal of Engineering Tribology, Part J, Arabian Journal of Science and Engineering, Industrial Lubrication and Tribology. He is also an active achiever, a reviewer of various reputed journals like Tribology International, Wear, Polymers, Defense Technology, Collides, Interfaces and Communication, Journal of Material Research and Technology, Material Research Express, Engineering Research Express, International Journal for Surface Science and Engineering, Friction, Journal of Engineering Tribology, Silicon, and many more. He has also delivered more than 25 invited talks, both at the national and international level, on composite materials, surface engineering, and machining. He has received the research grant from various government organizations such as MHRD, SCRB, for the various research activities. He has organized almost 5 different faculty development programs and short-term training programs on tribology and international tribology research. Recently, he has conducted a international ITRS, which is International Tribology Research Symposium, where people from 18 countries have participated with 275 research publications across the globe, and every presentation, every paper was given a chance to publish in 10 different journals which are of SCI and Scopus actually. So with this little introduction, I request Dr. Jitendra Katyar to deliver the session. Jiten, you have 1 hour 15 minutes, and last 15 minutes we will dedicate for the question answer session. And now you can start it.
Yeah, thank you, Dr. TVK Gupta, and thank you for your nice introduction. And I've not done that much work, whatever done by others, but still I am trying to do some work. So this is talk. Most probably, you have listened last 4 days continuously in the various aspects of the triple M, and now I am just introducing them tribological aspects in that particular machining or manufacturing, like how we can calculate reduce the friction and reduce the wear so that we can improve the wear resistance property of the material, and we can increase the material removal rate. So that is very important aspects in the manufacturing and machining. So today just I will go through it by adding the different hybrid nanoparticles inside that particular cutting fluid, and that we just use the minimum quality lubrication. That is very uh, important in that particular aspect. So minimum quality lubrication is very important nowadays, because that particular gives you the better insights rather than the wet or bulk cutting fluid if we are using. So this is a topic which I just cover in that particular 1.5 hours. So I just introduced the few basic things in that particular manufacturing. So what are the basic machining, why the machining is required, and what are the different types of the metal cutting processes, what are the various cutting parameters which are very important, and why the force analysis which we have performed in that particular machining, why that is very important. And then we just go for the cutting fluid importance, and I just show you the two case studies which is already published in the reputed journal, one in friction and another one in journal in manufacturing process, in the terms of metal cutting. So this metal cutting, as you know, that this is a one machining process, and from this machining process we just remove the material and we just shape a particular desired final product. And in this process, what we will do, we just remove excess material from the workpiece in the form of chip. So chips are generated in a larger way, and it is a most important manufacturing process in among all the manufacturing process. And by this process we can get their final shape, size, and metal removal, either in the way of directly or indirectly, both the way we can do it. So there are various types of the material removal process. One is called traditional process, advanced process. So traditional, we just go it in the metal cutting process, this turning. So traditional again divided into two groups, cutting and finishing. And this cutting further, either your object is circular shape or non-circular shape. According to that, we just choose the particular machining process. In finishing process also we can choose two types, either you are using the bonded abrasives or loose abrasives. Bonded abrasives like sindri paper, that is the cheapest one, and loose abrasive you just spray the particle like buffing, whatever you are doing like clapping and polishing. Advanced processes are nothing but or non-traditional or unconventional processes like electric discharge machining, electrochemical machining, electrochemical grinding, electric discharge grinding. So there are drilling. So these are the various kinds of the advanced processes where your tool and workpiece is not in contact. But in traditional process, your tool and workpiece is in a contact. That is very important. So when two bodies are in a contact, then always friction and wear happens. So the machining will performed by the two types of the cutting tool, single point cutting tool or multiple point cutting tool. So in single point cutting tool, it is basically used in lathe, shaper, planer like this. And multiple point cutting tool, it is drilling or milling. These are the things. So there is the very important parameter is how we can decide the feed in both types of the cutting tools. So in that particular cutting, single point cutting tool, that is per revolution, or in multiple cutting tool is feed per teeth, because there are the multiple teeth is there. So that's why the feed, whatever we have given, that is a feed per teeth, that is very important. This is the basic difference between these two types of the cutting tool. So important points which needs to be noted in that particular characteristics of this metal cutting is You can improve the dimensional accuracy and tolerances, and also you can achieve the internal or external features. Only drawbacks in that particular metal cutting is you can remove a large material from the surface as a form of chip, and those chips, the disposability issues is there. Most expensive among all the manufacturing process, this is the metal cutting process. So there are two types of the cutting, like 2D cutting or 3D cutting. So 2D cutting is known as orthogonal cutting, and 3D cutting is known as oblique cutting process. So in this, you can see the tool is having the tool as is inclination, with have some inclination with the workpiece, and it is the perpendicular with the cutting speed. So that is the only difference between this orthogonal cutting and three oblique cutting. So most of the experiment, whatever we have performed in normal workshop, that is all oblique cutting. So there are three forces acting over the surface, like turning, milling. These are the all we perform in oblique cutting. Only cutting, if you want to cut the two rod, then we go for the orthogonal cutting. So this is the least used process rather than the oblique cutting. So in metal cutting, there are various machining condition is there. So either what type of the workpiece material you want to turn, what type of the cutting tool, what is the cutting geometry, because the rake angle is widely important. So either your rake angle positive, negative, or zero rake angle. And then these are the principal cutting conditions. These are all four cutting conditions are very, very important: cutting speed, feed, and depth of cut. Nowadays, cutting fluid is also included in that particular one. So that's why Taylor's tool life equation, this BP power n is equal to constant. After that, they modified and include the feed and depth of cut also in that particular Taylor's tool life equation. And they just make some exponent, and that feed exponent is always greater than that depth exponent. So that is, these are the few important parameters in that particular cutting condition, which affects in the material removal rate and the wear of the tool surface. So why we need the machining or this calculation of the forces? So we just need the cutting. Why we use to analyze the cutting forces? That by using analyzing these forces, we can estimate the power requirement by the machine tool. So according to that, at least we can design our machine tool, and we can select the motors in that particular machine tool. So machine tool also we can design it static or dynamic stiffness. We can improve it by these calculation of the forces. You can improve the part accuracy. You can achieve part accuracy from the tool workpiece deflection also, because how much force it can exert according to the tool stiffness is also very, very important. Tool toughness. So tool toughness and tool strength is very, very important, so that it will not deflect. Because what happened, your tool is acting as a fixed cantilever, fixed beam cantilever, and one end is fixed and another end is having a consist of point load. So in that way, we just design the tool toughness and strength of that particular. So these are the few parameters, few design aspects in which your cutting force analysis is very, very important. That's why these cutting force analysis is important. So there are three zones in metal cutting. One is called as shearing zone. This is the shearing zone through which your material can deform and it can break and flow over the work surface. It can shear it and flow over the tool surface and move away. That is in the form of chip. And another zone is the chip tool interface. So this zone is very, very important, because this chip, when it's sheared from this shearing zone, then it is having a very high temperature. So due to that particular very high temperature, it can melt the material and diffuse some material over this chip, and that creates the crater wear over the rake surface and the flank wear over the flank surface. And then another is cutting forces, which connects by the workpiece to the cutting edge. So these are the three types of the three locations where the force analysis is very important. So this, how we'll do this force measurement, we just installed as our force dynamometer, and this is the tool. You can see here the sharp edge, and this is the rack face through which your chip is moving. And this force dynamometer having the three piezoelectric sensors. So these piezoelectric sensors, according to the deflection, whatever the deflection exerted by this tool through the workpiece, that can deflect according to these piezoelectric crystals, and these piezoelectric crystals gives you the output in the form of your voltage. So that voltage is either millivolt or some micron volt. So that will further converted into your force through that particular LabVIEW software. So this piezoelectric only gives you the signal in the form of voltage. So what forces is more in that particular turning operation? So according to that, this piezoelectric crystals deflected, and according to that, you will get the force or higher peak in that particular any direction, fx, fy, or fz. So that is a force measurement, and here piezoelectric crystals are widely used. So because why we use the piezoelectric crystal, it is very immediately it can sense the deflection. A small deflection also can be sensed by the piezoelectric crystals. So in this particular assumptions, how we can calculate the force. So we just know that the theory given by the Ernest Merchant in 1940, and they just calculate the force by using the 2D force analysis, that is known as orthogonal analysis, and they just perform by taking these assumptions. So they just assume that the basic assumptions, the tool is very sharp and no perpendicular to the velocity, no, and perfectly plastic and material is rigid. So these are the various assumptions taken by Ernest Merchant, and they just make a force analysis, and this force analysis they just make a circle. Why he choose the circle? Because you can see in the circle, each element, each forces are in a 90 degree. So we just know the ninth class theorem that if circle periphery 90 degree, then that particular your hypotenuse passes through the center of that particular circle. So that's why he chose the circle only, but that's why it is a Merchant circle, not any other geometry. So because all the angles on the periphery is 90 degree, and this resultant pass through the center of the circle. And after this, they can analyze the force analysis with terms of the shear force or rake angle. So these two you can calculate by using formula. FC and FT you can know by the force dynamometer, and you can calculate the shear force so that you can analyze the shear stresses and what are the other things. And you can also analyze the frictional force so that you can at least reduce the frictional force in some aspects. That is very important in travelogical aspects. So there are two types of the models which are used in that particular metal cutting. So primary shear zone, like a line. So this is line, and it is an area is the thick zone. So this is called a thick zone. So in thick zone, the analysis is performing is very complex. So what you will do, we just always select a thin zone model, and thin zone model is only currently used because thick zone model is only valid at very low speed and high depth of cut and feed. So if your condition is like this, then the thick zone model you can select it for the simulation. And if your speed is high and depth of cut is low and feed, then thin zone model is always select for the simulation. So this slide just only for the simulation purpose. If you want to do some simulation work in that particular tool chip interface, and what type of the model you will select it. So we just move to the chip to interaction. That is very, very important, because the second highest heat generation at the surface. Because of that, the craters wear happened over the tool. So how this things happen in 1970s? First time this chip tool interaction was studied by the scientist, French scientist, and in this particular study, what he did, he just take a transparent fire cutting tool so that he can observe each and every aspects, and it constructed to study the chip tool interface. So he observed that the chip material is sticking to the rake surfaces. First stick because of the high temperature, and because of high speed also this slide after some time. So due to this sticking happen, then sliding is happen. So sticking and sliding in between the material is diffused over the chip, this tool material. So that's why this crater wear is always away from that particular nose, because this nose temperature is very high. So here you can't get a crater wear, and but it is little away from the nose of your cutting or your cutting edge. This is the reason, because sticking region then sliding region. So when you stick, there is no material eliminated over the surface. But when it can try to slide after sticking, then the material is eliminated. So that is the basic reason in that particular two zones that is observed in chip tool interaction. So further, we just observed by the chip tool interaction by this IR camera and this optical profilometer. You can see that a little bit away from the region and sticking zone and then sliding zone. So the temperature at the sticking zone is more. That's why you can see at that very high temperature regime rather than in sliding regimes. So because of that region also the surface roughness varies over the surface. You can see that the sliding region, the surface roughness is more or less same, but in this sticking region there are so many peaks and valleys you can observe. So this mechanism is established in that particular Noruji Ferd and Hamedi in 2014 in International Journal of Machine Tool Manufactured in 2014. What he proposed that in a sticking zone, your asperities, all asperities are in a lock. So this, because of locking the temperature, whatever it says, it can transfer to the tool surface. Due to that temperature transfers, further it can affect the crater wear over the rake surface. And after in sliding zone, your locking is delocking, and your chip is slides over the surface. So that is main fundamentals, which is main schematic through which the mechanism of the chip tool interaction is given by this IJ-MTM. So further, we know that the cutting fluid, there are conventional wet machining, though we can use the flood cutting tool. So why we need the metal cutting fluid in that particular one? So first reason, you can remove the heat at the interface. You can easily remove the chips, reduce the tool wear, and also you can obtain the wetter surface finish. So that's why we just use the cutting fluid. And that is very, very important. Which type of the cutting fluid you can select it. Nowadays, because of the environmental issues, we are focusing on the biodegradable cutting fluid. So that is also necessary. You can use the vegetable oils by mixing of some this nanoparticle. That is also why we need to use the nanoparticle, because the nanoparticle is having better thermal conductivity. So thermal conductivity is very, very important to transfer the heat from the interface. So typical machining cost is used in tool changing 25%, coolant use 16%, tool 3%, downtime sometimes 7%, machining is 30%. So total wet machining, if you are doing, is this as the total cost which is involved in your final product. So major problem with the conventional process, like you will get if you are using flood cooling, then you will get a dirtness in your floor space, corrosion and contamination of lubricating systems, pollution and health hazards because the fume is generated. That fume is also creates skin cancer. Whoever operator working in that particular space, and it can also needs the storage and additional floor space, pumping system, recycling and disposable. So these are the few aspects. These are the few problems. That's why it is very important to move from the conventional cooling to the minimum quality lubrication, where 100 ml lubricant is enough for machining of 1 hour or 3 to 4 hours. So another aspects the tool material. So you just choose tool material and because what basic fundamentals is tool
It's
is
12
always
o'clock.
harder than the workpiece material. So what type of the workpiece you are turning or machining, according to that you just select the tool, and this is the according to the temperature range also, what temperature range you want to work. So you can select the tool material according to the hardness and temperature range in your work. So we just move to the minimum quality lubrication machining. So here, as I told you, we are using the very small quantity of lubrication, and that applied on the cutting zone. And this minimum quality lubrication is applied with the compressed air, along with the compressed air. So in that particular lubricant, you can add the nanoparticle. Those nanoparticle can impinge on this cutting tool. So that is the, and with the air. So normal consumption is restricted to 100 to 10 to 100 ml per hour according to our flow rate. What flow rate we have given. So optimum flow rate is also very important in minimum quality lubrication. Optimum pressure is very important. How much quantity of oil and air can be mixed, that is also affect in the our performance. So this is the widely used or current trend in that particular machining using of the minimum quality lubrication. Either you are working in a grinding, you are working in a milling, you are working in a shaping, planing, drilling, whatever. This minimum quality lubrication plays a very important role to avoid the flood cooling. So this minimum quality lubrication in terms of thermoelectric cooling systems also very important. So at the cutting temperature, you can see that feed, if you can increase the cutting temperature, is more or less same in that particular minimum quality lubrication. That's why it is also very great importance. So in case of dry, you can see the temperature range is very high, rather than the in flood cooling it will decrease further as the dry. But in minimum quality lubrication it is more as comparison to the both wet and dry. So that's why this minimum quality lubrication is widely used nowadays. And this is because your nozzle is highly impacted at the zone, that cutting zone. So that high impact cutting fluid reduce the temperature, and it can exerted the thermal conductivity, means whatever the temperature generated, it can try to easily cool because of the high temperature increment of the cutting fluid over the zone. So because of that reason, this minimum quality lubrication, that even though cutting feed rate is increased, your cutting temperature is more or less same in all the cases. So we just moved to our two case studies, what we did here in that particular SRM-IST. So in that particular first case study, why, as I told you, the why we use the nanoparticle inside the cutting fluid, because we need to increase the thermal conductivity. And why we need the increase the thermal conductivity, we can increase the heat transfer at the zone. So in this study, what I will do, I just use the graphite and talc nanoparticle, and we just mix with the coconut oil. So according to the this vegetable oils, this less fat acid and all the things in organic, so it can better provide the better lubricity property rather than the mineral oil and synthetic oils. So we just use the coconut oil because in southern region the coconut is available and it is easily available cutting fluid in that particular one, and that I perform on the titanium grade 5 that is used in a medical application. So this I developed in the 50-50% volume concentration of nanoparticle. So and after that, I performed the GRA analysis in that particular one because in titanium alloys, and we can from the GRA analysis, gray regression analysis, we can get the optimum output parameter. So main optimum output parameter is surface roughness and material removal rate. That are the two optimum output parameter which I consider in this study. So this is the lathe machine. I hope it will also in all places it is there. You can see that particular the dynamometer and this cutting tool and insert. We can make all the things and we perform the test. So this is the schematic of the MPL setup. So here dynamometer tool and you just machine it and that dynamometer gives you the data acquisition software connected with data acquisition software. So whatever the voltage signals comes from this dynamometer, it can convert it into the digital signals and you will get a digital reading. And further, this compressor, your compressed air goes and mixes inside this minimum quality setup pump and mix with the cutting fluid, and it can goes in, through the nozzle at the zone where it is required. So this is the basic experimental setup of your minimum quality lubrication. So these are the various factors which I consider in the three levels: 450, 800 RPM and feed rate. I have taking these 3.1 to 0.2 depth of cut and nanoparticle concentration. So 0.25 means 0.125 is concentration of graphite and 0.125 concentration of talc. Why I choose the graphite and talc? Because graphite gives the low coefficient of friction and talc is gives the high wear resistance property. Because of that reason, I have chosen the graphite and talc in that particular one, because I have seen and I have also published so many papers in that particular graphite and talc in my doctorate time. So because of that reason, I thought here also I can choose the graphite and talc and observe that particular factor in the output parameter. So these are the two machining response parameter: cutting forces and surface roughness. And we make a Taguchi analysis, total 9 experiments to perform it. And from all those 9 experiments, we can see, observe that the 450 RPM, 0.1 depth of cut, 0.1 mm revolution feed, and 0.25 nanoparticle concentration gives us lower forces, and also the surface roughness is lower. So after that, we perform the gray regression analysis, and by using this gray regression method, so we analyze the gray regression coefficient by this formula, and we just rank out. So 1 to 9, because 9 experiment, which is the most, so experimental 7 gives the most confident result and most appropriate result rather than the other one. So which response is better? So which one is the contribute more? That is also we just optimized in by using this gray regression. So this is the velocity. This is the source. This cut here. So this is the velocity that is in RPM. So this is only contributed 13%. Feed is contributed more in that particular force analysis, force and surface roughness. After that, feed depth of cut is very important. Nanoparticle concentration is also, but it is less than other 3 parameter. So these are the mean effect plot which we obtained by the GRA method. And here I obtained that 450 1 and 0.1 and 0.75, so maximum to the minimum. So that is the main thing. So these are the optimum parameter which obtained by the GRA method, and these optimum parameter we just perform this optimum parameter. We performed our test, and then also we can check the corresponding response values. Like because there are total three cross four, most of them total 81 experiments. So in between, I have checked the confirmation test. So that graphite talc nano fluid and pure coconut oil, you can see this optimum parameter. The forces is 68.6 and 86. So that is good. But in case, so in randomly, I select another parameter in that particular one. Maybe that will be also there because this GRA integrity, we can reduce the experiment. So that is a confirmation test also, either that is correct observation or not. So I perform this confirmation test and observe that the confirmation test and with optimal test obtained by the GRA within the range of 1 to 5%, that is acceptable range. And further, in terms of the surface roughness also, we can get it in that particular range. So this variation in the response parameter with respect to pure coconut oil, which I observed that the feed forces is 21.19% or 21.19% improves or reduced as comparison to the pure coconut oil, and surface roughness improves 18.9%. So that is the good results by using this graphite and talc nanoparticle. So these cutting edges also we can take the image from the parameters semi analysis, and you can see here in experimental 7 which obtained the lower force and lower surface roughness. You can see that the no flank wear or edge wear happened in that particular cutting edge. But in other cases, you can see that the very high wear over the cutting edge it is observed. And in the form of chip, also we can see that the segmented and segregated chips we obtain. This is because of the low thermal conductivity, high thermal conductivity, and other parameter in chip formation. So this chip, because of the segmented chips, is very important to increase the life of the tool. So this is automatically we will get by this optimum parameter. In optimized condition also we can get it these type of the segmented chips, but in other cases you can see the curly and segmented chips. So further we just perform the tribological test of nano cutting fluid. So this test only check the this lubrication property of your cutting fluid, whatever you want to use in that particular turning operation. So here I have a cylindrical pin that is made up of by the AISI 304 steel and your EN31 the disc. So that we just this is AISI 304 aluminum one, sorry. So this aluminum alloy and this pin we just tested over this pin on this carbometer only to validate the this nano cutting fluid. So this question, one reviewer asked this question, why you choose the aluminum one with EN31 steel disc? Why you have not chosen the titanium with the same environment, whatever you want to perform in the turning? So answer of this question, what I gave, and this reviewer was also satisfied, because I have observed in that particular several literature that if we use the titanium pin, then the searing problem in the titanium pin is very high, because that is very hard. So searing is not done in the titanium one. So because of that reason, we have not chosen, and that is also not recommended by the other reviewers. So in this, also we observed that after adding the nanoparticle inside the coconut oil, our coefficient of friction is reduced. And in case of 0.75% gives the better results in terms of coefficient of friction, which we observed in the turning operation also. And in case of 0.75, our wear of the pin is also very less. That we can check it by the pin surface morphology by SEM. And here you can see that the sliding scar and very high sliding wears over that particular pin with pure coconut oil. But when we added the graphite, because of the lubricity property of the graphite and talc, and graphite lower lubrication, higher lubrication, and wear, talc gives the high wear resistance. Because of that reason, you can see the very smooth surface over the pin by using the graphite and talc nanofluid in between that EN31 and the pin. So that is the observation by the tribological characteristic. And what is the possible mechanism which I proposed in this paper? That is because of the nanoparticle comes in between the tool and chip interface. Because of that reason, the surface roughness is also improved, and also it can easily move away from the workpiece surface, and it can take the heat from the chip and remove in that particular range, and it can reduce the forces because there is no direct contact between the chip and tool. In between the nanoparticles there. So that is the possible mechanism. Because of that reason, your life of the tool is also improved. You can reduce the cutting forces at the interface, and you can get the better surface finish in that particular turning operation. So this is the possible mechanism which I proposed it, and that paper is published in Journal of Manufacturing Process. So this is the overall conclusion which I observed, that the significant reduction in cutting forces, surface roughness by the 22% in cutting forces and 19% in terms of the surface roughness, and by this hybrid nano cutting fluid, and lower values of the friction coefficient has been observed by the 0.75 volume hybrid nano cutting fluid as comparison to the pure coconut oil. So another case study, we also use that alumina and MW70 hybrid nanoparticle on this tribological property in turning operation. So that turning operation we just perform on the aluminum alloy. So these are the time image of this your cutting fluid. You can see that's aluminum, how it looks like, and multi-wall carbon nanofluid. So this multi-wall carbon nanotubes also are uniformly distributed, and this hybrid one nano cutting fluids. These are observed by the transmission electron microscopy. So here also we just choose the 4 parameters in 3 levels. So cutting speed, we just varied 60 to 120. Cutting feed, depth of cut, nanoparticle concentration. And here I have used the RSM method. And in that particular RSM method, we perform the 27 experiment, and also we can obtain the response variable in the flank wear and the temperature at the interface. And this temperature at the interface is we can obtain by the thermocouples which we place by the K2 junction. So that K2 type thermocouple which is used in this study. So in this study, we just observe each and every parameter and observe the particular where we will get the lowest temperature at the zone and the lowest flank wear. So we just observe this 90 meter per minute, 0.08, 0.6, 0.75 nanoparticle concentration gives the better result in terms of the temperature, in terms of the flank wear. So minimize response parameter, what we will get in aluminum nanofluid, the minimize is the goal is the minimize the input variables like this, and minimize responses is 81.29 which observed. In case of the nano hybrid nano cutting particle, we just get the nodal temperature is 58.9 and tool flank wear is less. So apart from mono types of the cutting fluid, hybrid types of the nano cutting fluid is always better than in case of the machining, whatever the machining you are performing, drilling, milling, or grinding. So these are the tool images which can obtain for the various concentration of the nanoparticle. So 0.25 you can get it. The high flank wear in monotypes you will get in all the cases high flank wear, but in case of hybrid type, you will get a very low flank wear in case of this hybrid nanoparticle 1.25%. So this is the tool images, and in this way we can calculate the flank wear of these by these tool images. So travelogical results also we can do it for both type of the particle on the same setup pin on disk. Because here we use the aluminum one, so that's why there is no thing is required to explain. So here you can see the aluminum nano cutting fluid. It is coefficient of friction is greater than the hybrid cutting fluid. So initially, why hybrid cutting fluid shows the higher coefficient of friction? Because when two particle is there, so shearing takes place, and it can exert more pressure over the surface. Because of that reason, after that, what happened? This three body phenomena happen, and then it can easily roll it. Initially, your pin is slide over the particle, so that's why the coefficient of friction is high. But when after sliding, it can start rolling. So sliding, rolling friction is always lesser than the sliding friction. Because of that reason, your friction goes down at the interface and with respect to time. And wear is also less in case of the hybrid nano cutting fluid. So these are the surfaces which can obtain. These are the optimum results. You can see the no pits formation, very smooth surface apart from other concentration of the particle. This is optimized one. This is the 1.25% concentration. This is the 0.75 volume concentration. So these are the observation after the test, pin on disk test observed by this analysis. So these travelogical analysis over pin on disk is for only understanding the behavior of the cutting fluid, whatever we are using in the machining, through minimum quality lubrication. So this possible mechanism same is also here in that particular case, and this paper is also published in friction that impact factor is 5.2. So the conclusion from this results is by mixing the MWCNT and ammonia enhance the thermal conductivity also 0.26%. I have not shown the thermal conductivity result data here, but it is also I have done it, and it increase with the increase of the nanoparticle concentration. So by using the nanoparticle, we can increase the thermal conductivity, and that is very, very useful for the extraction of the heat at the interface. So hybrid nanofluid also shows the lower coefficient of friction as comparison to the monotype of the nanocutting fluid. So smallest contact angle also we can get it. That is also one reason. So we can, through which water contact angle wettability, we can say that the adhesive property, and which if your is more adhere to the surface, then it can provide the better lubricity like oil. So that is only reason we have performed the water contact angle also. So overall, we observed that the significant reduction of the 27.3% in the nodal temperature in case of the hybrid cutting fluid, and 11% reduction in the flank wear in case of the hybrid nano cutting fluid, aluminum and multi-wall carbon nanotube. So in this, in this type of the work, still various scope of the research is there. You can get it the very easily good publications in this area. You can analyze the influence of hybridization of different kinds of the nanoparticle in 50-50 proportion. You can also explore the various combination of nanoparticle in a various concentration also. Also, you can optimize the volume fraction of the nanoparticle in cutting fluid. You can study the you can study and develop the suitable nano cutting fluid for the superalloys like highness or titanium or inconel high entropy alloys. So because these are the different kinds of the alloy nowadays used in the various application aerospace and space industry. Additionally, you can also investigate to perform by considering the different shape, size, and concentration of nanoparticle in on the machining performance. And also you can optimize the parameter, further consider the optimization process by Taguchi or RSM to flow rate, spray distance, because that distance between nozzle and tool is also very, very important. So that is very important, like in abrasive water jet machining. If your nozzle is very far, then it can you will not get a good shape in abrasive water jet machining. So this distance between the nozzle and the tool interface is very important, and angle is also very important. What angle you will get it, so that also affect the machining performance. And air pressure for the minimum quality lubrication, you can these type of the things also it can be optimized. I have not seen so many papers in that particular area. So these are the various research scope in this field in metal cutting. So I have published two books, as initially sir said. These are the two books: Automotive Travelology and Travelology Influence and Application. If you are interested, you can read those two books. Several chapters are interest of yours, so maybe. So thank you very much. If you have any question, you can ask me.
Uh, Thank you, sir. Chaitanya, TVK sir student.
Yeah,
Sir,
Chaitanya.
yes, sir. Good morning, sir. Good morning. Sir is in
Good
office.
morning.
By the time sir reaches, we will have question and answer session, sir.
Okay, no issue.
Yes, sir. By the way, sir, it's a very nice and informative session. It went lively also. It's very good, sir. Actually, our participants are almost 80. So, all the participants, please, if you have any question, please write it in the chat box. Sir is ready to answer your questions.
If you want to interact, you can also ask.
Yes, yes, sir. I've unmuted all the participants. If anybody want to ask any question, sir is ready. Sir is available, and you can answer. You can ask questions. Okay.
Who is making the question? So Venkateswara Reddy is asked this: what is the size of nanoparticle in this study? So this size of nanoparticle is approximately 30 to 40 nanometer, not more than that. So at least you just choose this size is very wisely, so that you will get a better results. So this is the range of 30 to 40, or these are the two mix. So one particle talc size is a little bit higher, this 60 nanometer, in the range of 40 to 60 nanometer. Further, I just actually in chat box, it is very small here. It is showing.
Okay, let me read actually. Have you considered both plastic and elastic zone of the tool chip interface while cutting off ratio?
Actually, I have not performed this simulation work in that particular one. So this is totally experimental work. I just showed you that if you want to perform this simulation work in that particular cutting zone, then I showed you two types of the model. Either you can go for the thin shear zone model or thick shear zone model. So in thick shear zone model, you can consider both elastic and plastic, because the elastoplastic nature at the interface is more. But in experimental, it is observing is very tough.
Dr. Jita, have you shared our work recent publication?
No, sir, that I have.
Actually, recently we have published on Highness 25. We have done few experiments on turning with MQL. So there we have used the same gray relation, everything, and we have published. Recently, we got the publication actually. in the Journal of
Yeah, sir,
Engineering Research.
that I thought that the time is not less. So
Okay, okay. So there we
that's
have conducted minimum as I told in the morning session also, let the number of experiments be minimum. But if you do a in-depth study, no, you will get good publications. So we have done only 9 experiments, and with that 9 experiments, we are able to do the publication basically. Okay, there is one more. Adhesion takes place in the region adjacent to the cutting edge only, or in the all at the entire interface.
this because of the adhesion only you will get the flank wear. So how you can reduce the adhesion, that is very important.
Right.
Not for whole interface.
Okay, Professor Tangavelu is asking that he is working in the area of metal cutting and turning. Kindly help me to publish a journal paper. Okay. Anyway, sir, I will be sharing the email ID of Dr. Katyar, and either you can call him or.
You can share yours also, so
Huh?
you can share yours also because we are working.
Yeah. Actually, we have recently published 2, 3 papers together, myself and Katyar sir, with our group. So the 4th paper we are going to upload tomorrow actually. So we got the Journal of Alloys and Compounds, Material Science Engineering B, and Journal of Engineering Research. What else
So
we got?
my ID I can just share you again this simple one. You can see. You are able to see my ID.
Yeah. ID anywhere I will be sharing with the participants.
These are my 2 IDs. So this is my personal mail. So always try to
Use
mail
Gmail.
personal mail ID. So that is jitu1283@gmail.com.
I will be sharing your contact details also, but not the mobile number. Mail IDs I will be sharing with all the participants. If they have any specific queries, then they can write directly to you.
Yeah,
So,
no issue, sir.
So, Professor Tangavel, either you can contact Dr. Jitendra Katyar or myself, but there is an expert in the group, actually, Dr. Satish Chinchanikar. So, let me introduce, let me unmute everyone. There is Dr. Satish Chinchanikar, he is also from Kanpur. So, he is an expert in hard materials machining, actually. I should have.
Sir is here, sir.
Yeah, he is there.
I hope, sir, you are mute, then we can talk.
Good afternoon, sir. Good afternoon. I am from the start of the session from Monday. I have attended all the sessions.
All the sessions. Yeah, I have seen, sir. I have seen. Next time you will be the speaker.
Sir, Chinchinekar, sir, that is your area. I just move right now in this area.
You have done a very good work. I have seen the presentation and good questions also and good publications also. So nanoparticle area, really informative session. Thank you for that. Thank you, sir.
It's a pleasure. At least you listen my talk, sir.
Thank you, sir, Satish, sir. And can the sustainability issues be addressed in this research? There is a professor
regarding the biodegradability, that whatever the cutting fluid we are wants to use, that should be a biodegradable. So that is also, we just check it because graphite is biodegradable and coconut is also biodegradable. So this biodegradability comes under the sustainability aspect. So that is also in terms of biodegradability we addressed in that particular paper.
Okay. Any other questions, please? We have enough time. Any specific books, please guide.
For a specific book regarding what aspects?
Madam, you can unmute yourself and you can talk. Nanoparticles. She's asking about nanoparticles.
Yeah, can I speak?
Yeah, definitely.
Yes, sir. Sir, this is about the nanoparticles. If I want to work in that area, improving the wear properties and friction and how the adhesion will be of the foreign material in the parent material. like that. Is there any book we can refer to? Reference book?
Till now, didn't know, but I will check it and then I will share with you. Maybe you can
Yes.
write to me and in my mail ID. And I have not checked that regarding this
No
nanoparticle
issues,
aspect.
sir. No issues, no issues. I will write an email, personal mail to you, and
Okay.
maybe you can
I
guide
will,
me.
I will check it and then I will share you this regarding nanoparticle. But nanoparticle is the because the various nanoparticle have the different thermal conductivity.
Okay.
That is very important. What application you are targeting? What is the interface temperature? According to that, we just select the nanoparticle. We will not select the nanoparticle like that if thermal conductivity is very low, because aluminum has very low thermal conductivity. Graphite is more than that. So this thermal conductivity aspects is also very important in mixing all this. So according to that, we just use it.
Yes,
I
sir.
will surely I will tell you.
Yes, sir. Thank you. Yeah.
Okay. Any other question, please?
आई थिंक सर मुझे लगा कि बहुत जल्दी ज्यादा
खत्म
टाइम
हो
मैंने कर लिया और बहुत जल्दी खत्म हो गया ये.
फास्ट हो गया लगता है मुझे.
हाँ.
Right. Amit, you want any question?
1 घंटे में ही सब कुछ खत्म हो गया. मुझे आइडिया नहीं था कि 1 घंटे में आज खत्म हो जाएगा. I only say a few things to all. There is rumors like this in metal cutting. The research is exhausted. That is not true. If you will do some good work and if you use the modern technologies in metal cutting, then you will surely get a good publication. So nowadays, high entropy alloys, super alloys, highness, inconel, these are the various kinds of the alloy nowadays in market came, and very less publication in that particular areas. So if anybody can interest, you can work in these type of the alloys and various aspects in the nano cutting fluids is there. So in nano cutting fluids, when you prepare the biodegradability, you can check it. Stability of the nanoparticle is very important, because when you mix, then this because of the Brownian motion, it can settle down. So are the few things which is very important, and this stability aspects, at least in industry, it requires the more than 7 days, 8 days, not within 1 hour it will stable. So we just use the some surfactant also inside the cutting fluid so that we can improve the stability aspects. If we are moving to that part towards the uh, this vegetable oils, then the oxidation issue is more. So how you can reduce those oxidation, that is very very important. So this oxidative stability is very important in the case of the cutting fluid. So these are the still area is there, and you can explore further, and I hope you will get a very good publication in this area. And so many experts is there here. Satish Sinjanekar sir, he is my senior in IIT Kanpur, and he is the more experienced in that particular area rather than me. I tried in the travelological aspects more rather than the machining aspects. Because he did the so many experimental and numerical studies in that particular training area.
There is one more question. Is there any safety precaution you have to do while handling nano cutting fluids?
Safety precautions.
Ah,
Oh, safety precautions is nothing but you just here we just mix the 100 ml, and that we just use the ultrasonic homogenizer. So this by mixing half an hour or 1 hour, it is sufficient to mix nanoparticle inside the particular cutting fluid, whatever we use the base oil. So there is not that much safety precautions here. But at least if you wear the gloves, that is up to safe and up to you. But that is not major safety precautions is required to preparation of any cutting fluid. If you want to make a 1 liter or something, then you can use the stirrer. So that is also can be used to mixing the nano particle inside the fluid very homogeneously. And that is very, very important. If your particle is not homogeneous and cluster is there, then cluster is also acts as a sear, and then you will get the more wear over the surface. Because of that reason, when you increase the concentration of the nanoparticle, you will get the higher forces and poor surface roughness, because those nanoparticles also act as a shearing action. So that is the reason at the very high concentration you will get a poor surface finish and higher forces. So optimum concentration of nanoparticle is very, very important, so that each particle can roll easily. It cannot form a cluster in between that particular two chip interface.
Dr. Vikas Dwivedi want to ask something. His mic is on. Any other questions, please? Okay. What is the cost aspects for adaptability in industries for nano cutting fluids?
Actually, here we are using 1 gram or 2 gram in that particular cutting fluid, not more than that. So 100 ml is sufficient for 2 hours or 1 hour according to the flow rate of the minimum quality lubrication. So these nano cutting fluids is widely acceptable in all the industry, and slowly industries are moving towards the nano cutting fluid, and they are just moving towards the minimum quality lubrication, not flood cooling. So this cost aspect is not that much affect, because we are using only 2 or 3 gram of the any nanoparticle. That is sufficient for providing the better thermal conductivity.
Correct. Yeah. Any other questions, please?
I think, sir, everyone understand nicely all the aspects in turning.
Okay. If you don't have any questions, then we'll thank the speaker. This will be the end of. Okay. Can soybean or maize oils be used?
Yeah, surely it can be used. I have seen so many papers this soybean oils, maize oils, because soybean is unsaturated one organic compound, and it can also be used as a cutting fluid. In this, you can mix the nanoparticle, and you will get a better surface and surface finish and lower forces at the interface.
So any
So,
specific. Okay. Somebody is
so
asking
this.
any.
Yes, sir. I have seen that one, sir. So this, as I told you, soybean and this maize oil, this Malaysia. In Malaysia, there are widely used the palm oil. That is a biodegradable oil in the machining industries, because Malaysia is largest producer of the palm oil. So that is also a vegetable oil. So that is widely used in machining in there in Malaysia. So you will find the so many Malaysian papers on over the palm oil, and also they are using the soybean oil. So that's why initially I told you what region you are. According to that, you just select the base oil, because southern regions coconut oil is there, soybean is also easily available. So that is also means soybean is also having high thermal uh, conductivity and other aspects. Soybean is much better than the other base oils. So any specific nanolubricants for the non-ferrous material. So this I have not gone through, but as per my knowledge from the literature, I have seen that this graphite based or you can use this graphite or MW carbon based lubricant can use for a non-ferrous material also, or you can go for the hexagonal boron nitride.
Hexagonal boron nitride, I think somewhere we have seen actually.
Yeah, because one paper they have used for non-ferrous material for hexagonal boron nitride. So only difference between the graphite and hexagonal boron nitride, graphite is blackish in nature and boron nitride is white in nature. So widely acceptable, and you can easily see the color change and degradability aspects of the cutting fluid. So that is hexagonal boron nitride is same property as graphite because that is having a graphitical structure. This hexagonal boron nitride.
Yeah, thank you, Jiten. Any other specific questions? Okay, if you don't have any specific questions, then let me thank the speaker. Let us all thank the speaker for his wonderful presentation. And thank you, Dr. Jiten. And you can leave. I will have some small announcement to the participants. Oh, somebody is raised the hand. Just 1 second.
Okay, sir. No issues, sir.
Somebody has raised the hand. Who has raised?
I think unraised also.
Oh, unraised also. Okay, maybe solved, I think. Okay. Thank you then. Thank you very much. So, all the participants, we will be having the valedictory at 3 o'clock. I have just shared the link through email. I will be sharing the same on your WhatsApp also. And it will be for 15, maximum 15-20 minutes. But I request that some of the participants can give a feedback, a genuine feedback, whatever it is, positive or negative. Please talk in the feedback. And also, after the session is over, then we are going to meet again with the same link, and then we will discuss how to do the quiz. Okay. And thank you, everyone. Thank you for the your patience listening. Actually. Okay, Dr. Chitan. Thank you. I'll stop here. Actually, I'll stop here.
Thank you, sir. Thank you.